Welcome to Data Skeptic K-means clustering, the podcast exploring the problem, the algorithms, enhancements, and use cases for K-means clustering. Algorithms are continuously helping us improve more and more aspects of our lives and society and the way we run them. Algorithms are neither bad nor good. They're mathematics. Yet the results of algorithms can inform decisions that affect the lives of real people. Therefore, there's an increasing need for both scrutiny of the results and improvements to algorithms themselves to yield outputs that are more fair. When it comes to the unsupervised learning problem K-means clustering, it's reasonable for us to expect fair clustering results. Demand them even. I speak with Anshuman Chabra about the criteria for being fair and how his approach can achieve fairness.
Anshuman Chabra, University of California, Davis.
And can you tell me a little bit about your academic training? What did you study primarily?
I did my undergraduate in actually not computer science. I did my bachelor's in electronics and communication engineering. And from there on, I basically started my PhD in computer networks, which was more of an electronics related field, and then slowly shifted to machine learning because I got to go attend one of the top conferences. And, it really was something that I found, up my alley, so to say.
What were the aspects of machine learning, maybe the time and the place that made it the right thing to take a deeper interest in?
I always found it to be quite accessible in some ways. Knowledge is very readily available if you're willing to seek it out. I just found the community, just the ideas and the proliferation of these ideas and the rapid pace at which they were being proliferated to be something that I actually felt like, this is something that takes into account even networks right now. But if you were to look at distributed machine learning or like federated learning. So I feel like there's so many connections to all these subfields of computer science. And, research is happening at such a rapid pace. It just feels great to be a part of it.
What are some of your main focuses today for research?
My research and my thesis primarily looks at the robustness of machine learning models from two different perspectives. And the first perspective here is essentially adversarial robustness and how it is now commonly looked at in machine learning, which is, are my models secure from adversarial influence? Like, can they be, for whatever reason, if there is an adversary, can they disrupt the functioning of these models? And the second, which I find actually more interesting now, is social robustness. And that basically looks at whether these models are free from discrimination and, proliferation of bias and whether or not they discriminate against certain groups of people or individuals as a result of the predictions that they make. And I think both of these, there's also a lot of interplay between these two ideas and two perspectives. And I think that my research is kind of looking at different machine learning models where we can analyze these issues related to robustness.
I like this topic. I think it's an important one in machine learning, and I think most of our conversation today will focus on that second component you described, the social robustness. But while we're here, I'm wondering if I could ask you a little bit about adversarial robustness. What jumps to my mind immediately are these deep learning adversarial GANs, where I can get your model and I can generate something to fool you. Is that the main area, or are there other ways that adversarial attacks are applied in ML as well?
So I think that's a great question. In particular, I think this subfield got kickstarted because of, these deep neural networks where, we know very little of what's happening inside. And, you can basically craft these adversarial samples, like you said, and they can bring down the accuracy of this neural network to even zero. And I think in the general umbrella term for machine learning, where you have so many different models, adversarial robustness and adversarial examples can be very specific. So, for example, with like my specific interest line clustering, so here, what we would look at as an adversarial sample would be, can I maybe introduce certain samples into my test set or my, like online inference module where my clustering model, which was originally performing, I guess, satisfactorily, for whatever reason now, because this sample was so close to the decision boundary, it just flips it. And, now suddenly you have all these misclustering happening. And I think it's very application specific, but there's many different ways that you can define adversarial robustness depending on the model that you're using.
Yeah, definitely an area I hope to cover in future episodes in multiple facets. But today maybe we can zoom in on this social robustness. I think that sounds intuitively appealing, but from a more mathematical angle, what does it mean to be socially robust?
I think there are two general ideas here for what this fairness problem or the social robustness problem brings with it. And I think both of these have been very, I guess, extensively looked at for clustering, which is kind of my main area of focus in machine learning. So one of these, the first one is group level fairness, and the second one is individual level fairness. And, in layman terms, what that means is group level fairness implies how or whether or not certain groups of people that might comprise of your observations in your data set or samples in your data set are impacted as a result of the clustering outputs that your clustering algorithm or model might generate. And the individual fairness aspect is more, I guess, related to whether or not individual samples, like whether similar individual samples are treated in an equitable fashion. And I could also give examples for how these two differ in the clustering context. At least that's something that's of interest.
Absolutely. Yeah, an example would help if you want to go into that.
Yeah, so for group level fairness, let's say, and I'm going to stick with, for both of these examples, I'm going to stick with something, I guess, that most people would know about in the clustering community, which is k-means, probably one of the more famous algorithms out there for, data mining and data science. So let's say we have this problem where we want to shortlist candidates and, recruit them potentially for our company, and we want to use a clustering algorithm to do that. So we have this vast, maybe we have historical data, and we also have, like recent interviews and, recruitment, and we've basically got this large scale data set with a lot of features, and we don't have any attributes, obviously, for features that sort of signify things like race or gender or age, like no protected attributes of that sort. But what we will see is that if you were to say now cluster on all this data, and because of whatever historical bias that exists, you basically would get two cluster centroids. Let's say if we cluster into two groups and we basically want to select all the members in one particular cluster, we can look at the centroids, the mean values, and then select whatever cluster that would be. What we see though is that, because of this historical bias, that white males would be sort of over preferred in one cluster due to just, I guess, historical recruitment strategies and for, say certain jobs. And what ends up happening is that even though in recent times you had a lot of women, for example, applying for this role, they would not be preferred just because of how the patterns are being mined from this data set and how the bias is propagated through the data set. So I guess fair clustering in the group level sense would look at trying to have some kind of minimum and maximum bounds on the proportion of each group members showing up in these clusters.
When I think about fairness in other settings outside of clustering, like, some supervised learning approach, should this person get a loan, yes or no? If your training data comes from a system that is systematically discriminatory, then your output model is going to inherit that. And I have kind of a clear understanding there of how we apply fairness and what we want in an output. But then the k-means example, we're talking about the classic unsupervised learning case where, I don't know, there's something you throw caution to wind, you always get some clusters out. What do they mean? Are they fair? It feels a little less connected for me than the loan application problem where I see the tangible label. How does fairness play out, or what's the harm that could happen here if we're not very careful in the process?
So I think that, again, that's a great question. With supervised learning, you have these error rates for all your sensitive attributes in your classes, and you can actually kind of analyze, if this error rate is really high for certain protected groups or, sensitive attributes. For clustering, you don't really have those error rates because you don't have labels. And I guess that's why some of these definitions for fairness, while again very application specific, actually can only be understood in that particular application scenario. So for example, for individual fairness, one easy way to think about an example would be facility location problem where clustering is quite often used and you really don't again have labels. So this is a classic unsupervised problem. Here, what you would want to do is have, for example, let's say there are three regions that we have. One of them is a suburban area, so it's very sparse and it has a population of X. Then you have two city areas which are closer to each other but very dense. They both also individually have a population of X. Now, if for this facility location problem, say I wanted to open up hospitals for these regions, and I used something like k-means, again, what would happen is it would, just because of how it would try to minimize the variance within these clusters, what we would get is one cluster opened up for the two city areas right in between them because they're very dense. So the mean would inherently lie in between them. And the sparse suburban area would have two cluster centers opened up to cover this large area, even though all three areas have the exact same population. So the fair solution here would be to have one hospital opened up for each of these regions. But in that sense, I guess this solution that you would get from vanilla k-means is inherently unfair. And what you could do is then come up with an algorithm that is constrained to output in a mathematical sense for whatever fairness definition you have, to abide by it and to output clusters that would then be, according to that definition, fair.
So if k-means poses some challenges for fairness, guess that was maybe one of the motivations to explore hierarchical agglomerated clustering. Can you talk a little bit about that algorithm and the choice to explore it?
So hierarchical clustering is inherently a little bit of a different problem compared to k-means, which would be technically called a flat clustering algorithm. And one could think about hierarchical clustering as essentially a hierarchy of clusters themselves. So you basically look at, say, you have n samples in your data set. You have now a tree of possible clusters where the leaves or the lowest level of that tree are all those individual samples, and they all constitute one cluster. And then you keep iteratively merging them to create this tree and create this tree where, clusters are reducing at each level, where eventually at the top or the root node, what you would get is one cluster containing all the samples of your data set. So in this way, you kind of have this flexibility of a lot of different clustering choices, whereas in k-means, you kind of fix this k a priori. And for fairness, I think this problem, just extends to also being unfair in a certain sense. So I guess in our paper, what we wanted to look at was, can we develop an algorithm that builds on top of the more traditional hierarchical clustering algorithm to essentially give us this trade-off between utility and fairness for any definitions of fairness. So if you think something makes sense, if you want to, say, have a certain output or proportion of protected group members outputted in your clustering output, can we come up with an algorithm that allows us to do that?
Well, I want to get into your algorithm specifically, but one quick question for you while we've got this tree concept in our mind. I prefer hierarchical clustering in a way, knowing that I get this tree data structure back. It just seems like a more rich, informative data structure I can do some things with. Yet, k-means gives me a pretty, it's a label. It's a very simple thing to now make some if statements against. What do I do with that tree in practice?
I think what we would think about, hierarchical clusters and the outputs of hierarchical clustering algorithms, think about it as running k-means for a wide number of k values, and from basically starting from 1 to n, where n is all the samples in your data set. And basically what you're getting is, even though there's this underlying tree structure, what you do get is essentially a number of different settings for k. So you still get those labels, and you can maybe figure out based on how, for your application, what makes sense, which k looks good to you. And if you're not sure about that, I think hierarchical clustering is a great choice, because you have this entire tree of clusters, whereas for k-means, you would have to run this algorithm multiple times over, and you would still not maybe get like a fixed agglomerative merging of these clusters. So you wouldn't really get this tree structure where you can actually see how clusters were merged together. So you also now get the relationship between points and how they come together and form clusters. And I think this is something that's very widely used in genetics and classification of different species, because you can actually see how similar species might be grouped together. And I think that's, in biology, hierarchical clustering is quite useful because of that reason.
Well, if the output we're looking for is a tree, then, I know trees have all these properties about being enumerable, and we could get into the combinatorics of it, and one tree is better than another tree. Independent of fairness, which obviously we want to get into, prior to having that concern top of mind, how is this search optimized? What's the best tree we're looking for?
So, what the outputs are usually represented as for hierarchical clusters are actually a specific kind of tree, which is known as a dendrogram. So, what you would see is basically each level of this tree represents merges made between the clusters at that point of time, and how that leads to a new cluster being created. And then this kind of keeps happening as we keep going up in the tree. And I guess in some sense, even though mathematically this tree concept is what we're looking for, most packages and algorithms that you would get for doing hierarchical clustering would basically give you an output that is very much still labels, but you just get like a dictionary of all labels to iterate over.
And if we want to now optimize that structure to give us a more fair result, how do we express that from a mathematical optimization point of view?
One way that we looked at was maybe, you figure out which k makes sense. And by k, I mean the number of clusters that make sense for your application. And then you want to also enforce fairness for that level of the tree. One way to think about that would be to kind of translate this idea of fairness, group level fairness that we've seen in flat clustering onto this level of the tree. And for flat clustering approaches, there are a number of different algorithms or, constraints that we can impose on traditional algorithms to generate a fair outputs. And I think the first one, which is basically what sort of inspired a lot of recent work, is something that we call fair decomposition, which is published in Europe in 2017, which specifically looks at trying to figure out if we can find some microstructures or microclusters, which the authors term fairlets, in our data set. And once we are able to do that, if we were to consider those as the units or the samples that we want to cluster on, then basically when you pass this into a vanilla clustering algorithm or a flat clustering algorithm like k-means, the output that you get, because those individual units are themselves fair, will be overall be fair. And that's something that we've seen also being applied to now hierarchical clustering, where certain authors have looked at applying this kind of fairly decomposition to correlation clustering. So I think the technique of finding these kind of micro clusters that are fair and then sort of grouping them together using the vanilla clustering approach is quite fascinating. This is what would constitute a pre-processing fairness approach, where you don't really change the original clustering algorithm. You have this pre-processing step where you kind of find these fairlets, and then you use those to sort of get an output that is fair.
Very interesting.
Yeah. And for what we have done in our work, the approach that we're looking at is slightly different in that sense, because fairly decomposition, while a very attractive mathematical idea, is restrictive in some ways in that it's very non-trivial. Like it would be hard to figure out fairly decomposition for any arbitrary fairness metric. And so what we wanted to do was look at an in-processing approach to fairness, where you have this hierarchical clustering algorithm, which basically does agglomerative merges between subclusters to eventually give you this hierarchical clustering output. What we wanted to do was figure out if we can trade off this utility, which is basically like based on some distance criteria, with fairness, and just optimize for whatever input fairness criteria that you might have, and solve this problem in like a black box optimization fashion. And so we get empirically better results in that sense, which is I guess just a different flavor of the same problem.
And what data sets are you testing against for those empirical results?
In general, for fairness in clustering and even in supervised learning, there are a number of data sets that have been, that you would consider as baselines for testing, and then you can compare with other approaches as well. Most of these are basically related to samples that come from human beings themselves. So you would look at a data set that, for example, looks at bank data, which, has individuals basically whether or not they were given a loan, for example, right? And whether or not they were preferred over other individuals. And you also, in this data set, have features such as ethnicity, whether individuals are married or not. And you can kind of hide these from your clustering feature set and then measure whether or not they're unfair to that particular sensitive attribute that you didn't really cluster on. And you can kind of do this with a lot of different data sets. There's a credit card data set that where, again, it's like very similar in the sense that individuals are being preferred over other individuals for credit card offers. And you kind of get to see different flavors of this in kind of all of the data sets that we would consider.
Today's data lives in the cloud, so your business needs a cloud-native, next-generation solution for intelligent, accessible data analytics. Astrato is a modern BI solution for modern BI teams. Your organization's data already lives in the cloud, which means you can access the single source of truth. Astrato accesses your data where it already lives with a live query approach, so there's no need for data movement, ever. You maintain the agility, speed, and elasticity that modern cloud data warehouses deliver. Astrato's gallery of examples will give you a quick impression of the power Astrato can give your team. The sales workbook example gives me a good indication of the quality of dashboard I can create for my collaborators. And the Tour de France workshop shows off a few other features on competitive cycling data that I could see being really inspiring on implementation for when I have a demanding executive that needs to really slice and dice the data in a lot of custom ways. When I first started exploring Astrato, I connected a Google Sheet of one of my data sets just so I could kick the tires. After that, integrating with Snowflake as a backend was super easy. You'll find that integration to be pretty painless and definitely worth your time checking out if you're a Snowflake user. With Astrato, you can bring complex data to life with no coding skills necessary. To learn more, visit astrato.io/dataskeptic. Astrato is ASTRATO. Astrato.io/dataskeptic. Thanks to our sponsor BB Edit from Bare Bones Software. If you're a Mac user and you have any need whatsoever for a text editor, which, let's face it, that's got to be all of us, you have got to check out BB Edit. BB Edit 14 provides Mac users the most powerful, professional-grade text editor around. It's known as capable and rock solid, and can process files that are large enough to bring other editors to their knees. This tool's been beloved for over 25 years, and I can understand why. If I'm just typing up some simple hello world, I guess any text editor will do. But when I really get into the weeds and need to do some data processing, maybe I've got a big messy file, I need to find all the non-ASCII characters and remove them, BBEdit's there for me. It has best-of-breed multi-file search and replace and great scripting support for text transformations. There's a whole menu of text transformations that you'll find handy. If you're a serious data scientist or software engineer, you're going to bump into situations where you need a powerful text editor. So download and try BBEdit today. You can get it at www.barebones.com. See how much your productivity can increase. barebones.com and download BBEdit. Well, that process of withholding a feature and comparing it for a baseline, I think, is an important operation a lot of machine learning engineers are thinking about as they build models. They're also thinking about things like overfitting, right? For any model you build, look at a few metrics and decide, have you overfit? Do you have a sense of how much time you think people should responsibly be allocating for, compared to how much time we're checking for overfits, we should be checking for fairness and these criteria in our work?
I do think that, the latter is equally, or if not even more important than the former, which is basically related to accuracy. And in some sense, there is always this trade-off that you look at with, accuracy and fairness. And I think this kind of comes into play, especially when you try to impose these fairness constraints and you see model outputs, somewhat becoming lower on the accuracy side. So you might actually, by imposing these constraints, might lead to a model that is, like going to give you a certain output that is fair, but, at the cost of utility, which is basically however you would define the accuracy metric. And I think as scientists or as, like engineers working towards machine learning models, the eventual goal is for widespread adoption of these models. And I feel if fairness is not considered, that is inevitably going to fail because, if it's going to discriminate against any particular sect or group or demographic of society, people are not going to be using this model. And we've seen it happen before with, Microsoft's Tay chatbot, which became, was an online Twitter bot that you could train on user inputs, and Microsoft had to take it down really quickly because it became based on user inputs became quite toxic and quite sexist. And I think the point is, if the engineers had accounted for that kind of constraint or those fairness constraints on that chatbot, maybe it would not have been learning a particular kind of, it might have been actively trying to avoid that bias. And I think that's kind of what is really important here.
When you compare your results for clustering across some of those canonical data sets we'd mentioned, can we compare and contrast the results you get into the, what would happen with other algorithms or things that weren't taking fairness into account? Do I have to pay a big penalty to achieve this accolade?
So I think that's quite specific to how much you're willing to trade off. So for example, if you want a perfect output of, all groups should be represented exactly equally, you're going to be trading off more in terms of your utility. But I do feel that depending on a lot of these approaches that either we've developed or other people have developed, there is this kind of, like trade-off that, one can actually actively figure out would be suitable for a given application. And I think in some ways, we don't even need to start thinking about it as a trade-off. This is just how models should be. Like we should be looking at models that are fair. And, that's kind of what we should be optimizing for. And then we can try to maximize utility or accuracy as best as we can. But I don't think like thinking about this kind of trade-off in a negative sense would help sort of the long-term adoption of these models. And that's kind of, I think, what the main crux of all this fairness research is.
And when you think about the outputs of these clusters, I know one common use case could be marketing, which is an interesting dichotomy against the desire to be fair, especially when I think about age. Age does correlate with wealth. We all start from maybe not the same fair starting point, but generally people acquire wealth throughout their lifetime. So your interest in having a mortgage will come online at some point. Your interest in retirement happens a little later. That's a useful feature that maybe we want clustering to rely on, but it's also a social consideration we might be balancing against. How do we know the right way to approach it, given that some things we want well balanced and some things are a natural feature of the data?
So I personally feel that this design of these systems and their fairness properties don't just happen in isolation with computer scientists or engineers. I do feel that there is this social science component to a lot of these problems, and there are a lot of studies done that sort of indicate what would constitute an equitable approach or what would constitute a fair approach in the social sciences. And I feel there's a lot of things that we could borrow from these studies and then design computer systems that are also aware aware of, whether or not they'd be discriminating against certain groups. And to be specific for your example, where, age is of concern, I would say that maybe having age being considered here is not too bad, but if one were to think about it, it also depends on the extremity of these models and how they use that age factor. So for example, if all the predictions being made favor only people above a certain age, maybe there can be accommodations made to make it slightly more conducive to also other groups, and maybe people who are younger. And in that sense, I think that's why this whole idea of clusters being balanced is something that is very popular in fairness literature with regards to clustering, where you could have cluster outputs sort of representing at least a minimum number or minimum proportion of protected group members.
Well, to the best of my knowledge, there is not too much legal or compliance regulation around this sort of thing. I mean, there's GDPR and no law that says you must use logistic regression or you can't use it or these sorts of constraints. Do you think there needs to be a step in that direction? Should we have legal and compliance regulatory things, or is this something that industries can self-police?
I personally believe that this is a collaborative effort. Some of these ideas of fairness, if one were to think about only industry being in charge of something like this, I believe, because of vested interests, where, for example, user engagement is the primary metric for optimization, you wouldn't necessarily always want to be fair if it doesn't hurt your self-interest by that much. And I think that's where, some outside external regulation is also important. And again, this is something that needs to be discussed and needs to be certain as to how much of external regulation should be required. But I do feel that some amount of external regulation would actually help in, keeping sort of the industry machine learning models in check.
Well, let's imagine that there's a listener who, in their organization or job or project, is doing some k-means clustering today, and their data set does cover a certain PII features or something along those lines where the social impacts could be relevant, and they'd like to try out hierarchical agglomerative clustering with your fairness algorithm in place to see what their results might be. Could you talk through the steps of going from the desire to do this through how I get my final code implemented and a nice result?
Yeah, of course. I guess one of the shifts would be in trying to now, instead of working with this predetermined K, first generating this entire tree. So basically, our algorithm is also built on top of the traditional hierarchical agglomerative clustering approach, which is somewhat heuristic, but tends to work well in practice. And there, what we would like to do is essentially have some parameters that define how much fairness you are willing to and how much you're willing to forego on the utility. These can be figured out. We have an optimization procedure that runs before you kind of train this model that kind of tries to figure out what these parameters should be. Or you could also, depending on your application, because if you're a domain expert, you might know what those parameters might be. And you input those, and then our approach just runs on top of the traditional hierarchical agglomerative clustering algorithm to give you a tree of clusters where, for that K that you had in mind, we would see fairness enforced. And you could also do this for the whole tree. So where, we would be looking at for each of these possible levels of the tree, for each of these possible values of K, we would see fairness enforced. And in that sense, we could have clustering outputs that you could now use if you want that kind of rich representation for clusters. You could have many different clusters as part of your application, or you could look at that specific level of the tree and then just replace that with whatever outputs you had from K-beans before. And you would now see this output being fair.
Well, we've talked mostly about this algorithmic approach. I'd also like to talk about one of your other papers I'd read and this idea of doing antidote data. Could you extrapolate on what the problem is and how that's an appropriate solution?
This approach actually also pertains to what we talked about before on adversarial robustness. So since my work was kind of looking at both of these perspectives on robustness, I was wondering whether there is some possibility for interplay between these two ideas. And I guess one of them would be inspired by these kind of adversarial examples that we were seeing for neural networks and even, for clustering algorithms in recent times. We decided to think about this problem as this fairness problem as maybe if adversarial samples can be used to reduce the accuracy or disrupt these clustering algorithms or machine learning models, can they also be used to improve the fairness for whatever reason? And I guess our work kind of looked at introducing new data points that we call antidote data points. So these are essentially dummy points. They don't really have any real world significance tokens, but they're computed in such a way that when you add them to your original data set, the output clusters that you would see would be fair with, and again, this can be any fairness metric you can define for center-based clustering. You would see the outputs being fair with respect to that fairness metric for your original data set. So in this way, this is kind of a more, again, a pre-processing approach, but it is more general because you don't need to do fair decomposition that gives you an analytical guarantee for that particular fairness notion. You would have to do this for like each fairness notion individually. Whereas for our approach, you just have this algorithm and you figure out how to compute these antidote points. You add those antidote points to your original data set and now cluster on this combined data set. And what you will see is that the outputs that you get are fair with respect to your original points. And I think that's kind of, it's a slight deviation from the norm and how fair clustering has been approached so far.
And is there a key intuition for how it decides which data points to invent? How does it know what features are important?
So for k-means, what one would want to look at is, for example, if you want to make k-means fair, and your fairness definition is, again, this notion of balance, what we would do is this works in two steps, the algorithm that we proposed. The first one is to figure out what centers would actually make your solution fair. So we're kind of, and then again, we can think about essentially what would be some ways to maybe figure out centers that would be, fair. And then we kind of, by adding these points are computed to realize those centers. So in some ways, we're guessing as to what through this optimization process, iteratively guessing, and we keep converging to what would be good, fair centers. And then we realize them simultaneously by adding points that shift the centroids in that direction.
Makes sense. Well, I'm curious how your focus became about specifically clustering and fairness. This is an interesting intersection. What brought you here?
Originally, since I was working in networks and wireless networks to be specific, this problem of clustering is quite actively used there to figure out what sensors should be grouped together and how we can maybe optimize our algorithms by having cluster heads or these kind of device heads that could be used to maybe propagate information throughout the network. And an important problem that often comes up is how can you do that in a fair way? And what that fairness obviously has a different connotation in that context, but what it means is, can we maybe do this in a way that all devices are covered equally, and we're going to be able to sort of get some kind of proportionality represented there as well in these cluster heads that we've selected. And I think when I did start working on machine learning, this clustering idea was quite close to me, and I was quite interested in sort of exploring it more, especially in a more analytical way. And then fairness just kind of flew naturally from these wireless network problems that I'd looked at. And but now instead of devices in the network, we're looking at actual people, so the stakes are much higher and the problems become much harder. So I think that is kind of how it happened to be.
And what's next in your research? Is there anything up and coming you're excited about that you can tease here?
Yes, of course. I am actually now, in terms of this social robustness problem that we've talked about, looking at real world black box systems. So, for example, clustering, while, quite prevalent, might not have these kind of very specific real world cases of, being employed in pipelines where fairness might be of a huge concern. However, a lot of these black box production level systems like social media platforms like YouTube, Facebook, Reddit inherently use recommendation systems and machine learning models in the back end. But unfortunately, the only way you can query these models is through black box access. You don't really get access to YouTube's machine learning model. All you can do is watch some videos and then observe the output. So I guess some of the problems of interest here are also to analyze the possibility of bias or like fairness in these issues in these production level models through this black box query access. And then, basically figure out if there are ways to intervene or have like an intervention approach for these models. So that's kind of what I've been working on.
Well, very interesting ideas. I look forward to following and seeing where that goes. Where can listeners follow you online?
I have my website, and I generally planning to be more active on Twitter, but I do have a Twitter handle, and I also have a blog that I sometimes write on. But in general, I think the best place to find me would be Google Scholar, where I have papers coming out, or if I'm going to be speaking at a conference, which will probably show up on my website as well.
We'll have links to all that in the show notes. Anshuman, thank you so much for coming on Data Skeptic.
Thanks so much, Kyle. It was a blast.
That concludes another installment of Data Skeptic K-Means. Thanks to our sponsors today, Estrato and BB Edit by Barebones Software. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, show notes written by David Abembe, and our host, Kyle Polich.